Welcome everyone to our Wednesday ITMP research seminar. And today we have Viktor Mishnyakov from NORDITA, who will present on his new work on the matrix models.
Okay. Yes, thanks for the introduction. So, yes, I'm going to talk about Qt deformed matrix models, and this is based on a work that is almost finished and is hopefully will come out maybe like next week, maybe next 2 weeks with Laguerre. So, yeah, let's dive right in. Okay. Yes. So the plan of the talk is, well, that's kind of just an approximate scheme of how I'm going to go. I'll first explain the setup and then go to something called classical matrix models, the matrix models that most people are familiar with. And then I'll explain, well, the results and the recursions for Qt deformed matrix models and the role of the quantum toroidal algebra in all of this business. So in the setup, I want to basically explain what kind of integrals we're considering and where they appear. So the integrals that we are talking about are, well, they look pretty massive, but so let me first explain the ingredients of the formula that is written on top of the slide. So under the integral, we have a few objects. So the measure of this integral is given by something called delta qt of x. So first of all, it's an n-fold. Sorry, I didn't kind of. I should have put a product over dxi. So it's an n-fold integral. The capital N will denote the number of variables. So everything depends on these variables xi, which we integrate. So this delta qt is an important part of the measure. It's something that is the Qt deformation of the Vandermonde determinant, which we'll see. We'll see the Vandermonde determinant a bit later. Then typically this piece, this piece xi log t over log q is not included in this Vandermonde determinant, but I just kind of put it here to make the formula fit on the slide. So then, so this part of the measure kind of corresponds to how these variables xi and xj interact between each other. So in the classical matrix models, this corresponds to the Vandermonde determinants once again. But then there is also the analog of the potential of the classical matrix models. This is given by a product over all I of factors like this. And so here we have first a product over these Q-Pochhammer symbols, which are defined over here. So for those that are not familiar with these notations, and then the Pochhammer symbols in the numerator with parameters UA. So there's a sum of over A from 1 to NF. And then there are some Q-Pochhammer symbols in the denominator with parameters V, A bar, with A bar going from 1 to NF bar. And then, so there's exponent of log squared, and then there's an extra term xi to the log r over log cubed. So this is going to be the measure against which we are going to integrate any function, but in principle, we're going to focus on integrating symmetric functions because, well, that's how they appear usually, and also the measure is symmetric under permutations of all the variables, so we'll choose the functions to be symmetric as well. So f is any function, and we'll call this the expectation value of f in this Qt deformed matrix model. And then we'll label these different expectation values by kind of the parameters that enter the potential. So here I just wrote NF bar, but in principle, we could also label it by this L and R. So, well, depending on the situation, the label will be a bit different. And so finally, let me say, finally on the technical side, I also something that I kind of omitted here. I will actually assume that these expectation values, that this measure, that there is a normalization factor, which I didn't include over here for shortness, but I will assume that the expectation value of 1, so when we input a constant function over here, is normalized to be simply 1. So, yeah, so this is what we're going to deal with. And before we deal with it, let us ask where such objects appear. So there is actually many places in which these integrals appear in mathematical physics, in theoretical physics. And well, so I'm not going to list all of them, but I focus on 3, maybe the most important ones, which are part of a triality between different theories in a sort of AGT-like or BPS-CFT-like context. So first, and sort of the base point in the triality for us, meaning that we're going to label our models by where they sit in this first table, is that these integrals actually appear in the as a result of supersymmetric localization of 3-dimensional n equals 2 gauge theories with a bunch of fundamental and anti-fundamental matter, and also an adjoint multiplet on a geometry that is something that is this squashed half sphere. So it's a D2 fibration over S1, where the fibration, the Q parameter corresponds to how this D2 rotates when it's fibered along the S1. So there's a dictionary between parameters of the gauge theory and the resulting supersymmetric, the result of the supersymmetric localization. So n, the number of variables, is exactly the gauge rank, which how it usually appears. So UA and VA, so VA bar, there should be VA bar. They correspond to fundamental and anti-fundamental masses. They're not exactly the masses. There's something like exponent of the mass. So T is the adjoint mass. Q, as I said, is the parameter that corresponds to the geometry, the Gaussian parameter. And then you can also add a Chern-Simons term. So L is going to be Chern-Simons level, and R is the Fayet-Iliopoulos parameter. So actually going back, we can sort of tell that, well, as I said, so this L corresponds to the Chern-Simons level. And so this term here actually corresponds to the Chern-Simons contribution. So these two terms clearly correspond to the contributions of the matter multiplets, and this delta QT is what corresponds to the contribution of the gauge plus adjoint gauge fields and the adjoint matter. So, and therefore it has the T inside of here. And so, well, this describes the measure, and then obviously we can also ask to compute observables in this theory, and this will correspond to insertions of different realities. Is a two-dimensional conformal theory, but a Q-deformed version of it. So, well, I'm not going to explain in any detail what this is, but the Virasoro algebra has a well-known Q deformation, and one can construct Q vertex operators for it, so a full Q deformed free field formalism, and therefore one can define Q Virasoro conformal blocks, and compute them in a Q deformed version of the Dovzhenko-Fateev free field formalism. And in fact, such computation will lead exactly to the integrals that I was showing, where now it's going to be in. So yeah, there are some limitations. So in that case, the number of fundamental and anti-fundamental multiplets, well, the number of terms corresponding to the multiplets in the 3D theory should actually be equal. So I just denote them by NF. And such an integral will give an NF plus 2 point function. an f+2 point function, and then n is the number of screening charges, q is the q deformation, and so then the charges or the corresponding dimensions of the operators are sort of parameterized together with the position. So the positions of the operators are parameterized by z, while the charges are sort of parameterized by u, and so it's u over z. So alpha I are the charges, and then r is actually the charge of the field at 0. And so the central charge of this theory is expressed via something called beta, which does refer to the beta in beta ensembles. But this, in general, this beta is just a ratio of log t over log q, and then the central charge is expressed in terms of this. So there's an exact dictionary, and so the duality. For now, we have a duality between these two theories on the sort of technical level, or on the level of sort of exact answers, is realized as essentially as an explicit equality between these two. So these two integrals, or these two objects, are given by the same exact integral. So, well, in fact, since this number of screening charges in this case should be n, which is kind of an integer, we want to think of it as an integer, especially from the matrix model point of view. There are certain integrality conditions on the central charge, or sorry, on the charges on dimensions of the operators. So if you want to consider a general conform block, it's sort of an analytic continuation of what we're calculating here. And then the last corner of this triality is 5-dimensional gauge theory, and this is exactly an IGT correspondence between the 5-dimensional gauge theory and the Q-deformed 2-dimensional conformal field theory. So now on this side we'll have a gauge theory with a U and F gauge group in the 5-dimensional omega background. So Q and T are now exponents of equivariant parameters. And so, well, again, I'm not going to go into details, and this is actually all described in this paper here at the top, where it's worked out, and then there are also references to kind of the physics interpretations. So this integral is not exactly as it is not exactly, doesn't exactly give any Krasov function of this 5D gauge theory, but it kind of gives a sort of cut-off version of it, and it actually corresponds to a 5D gauge theory where certain parameters, mainly the Coulomb branch parameters and masses, are tuned in a certain way. And there's the physics side of it, which I'll not go into, but that kind of on the level of expressions, again, what it does is the standard Nekrasov function is an expansion in terms of tuples of partitions. So these tuples of partitions, they label fixed points in the instanton moduli spaces. So they so this is also a result of supersymmetric localization, and the whole instanton partition function is a sum over all fixed points, and hence over all possible tuples of partitions. The number of partitions in the tuple is fixed by the gauge group, but the partitions themselves can be whatever. So from the smallest to infinity. But actually, in this kind of specially tuned parameters, it turns out that the length of these partitions is bounded by n, this capital N over here, and then and so this is exactly the type of function that appears from the integrals that I was describing. So these kind of instanton-like sums are actually the result of a residue computation. So if we were to sort of write and to compute this integral, but sort of, well, yeah, to write a series sum over residue solution to this integral, this would exactly give this this instanton-like sum, and the residues are equal to the Nekrasov factors. So I mean, it's not just a kind of a qualitative, but a quantitative equality as well. And so this involves some peculiarities because, well, one has to show that the residues of this integral are actually labeled by tuples of partitions, which I'll not discuss here. But again, I can refer to this paper. And then, but yeah, so naively, what I can say is that naively the poles come from these denominators. So these are Pagamer symbols, so they're infinite products. So hence there's kind of an infinite number of poles really. But there are also zeros and poles in this delta QT factor, which can cancel some of the poles here. So yes, so there's a bit of a complicated count, but eventually it works out. So actually, the question of how to choose a contour of integration in this integral in general, and well, how this affects the result of integration is quite a complicated one. And so I will actually restrict to well, in some sense, it's a very small family of integrals of this type, which correspond to models with just a few number of matter and anti-fundamental matter multiplets, so less or equal than 2. And I will explain on the example of classical matrix models, or actually even finite dimensional integral, or sort of one variable integrals, why this restriction works. And I will not go into details to explain like how this restriction is important specifically in these integrals. But I'll explain the idea on a much simpler example. And then maybe standing a bit apart is a very special representative of this family of integrals, which has a separate a separate physical interpretation, is something called the refined Chern-Simons theory, which was proposed by Aganagich and Shakirov. Well, they kind of define this theory in some way by formulating the usual Chern-Simons theory in terms of modular matrices, and then finding a proper T deformation of it. There's no kind of direct Lagrangian for the refined Chern-Simons theory, but it's, well, widely accepted to be something meaningful. So the usual Chern-Simons theory and the Chern-Simons matrix model is what one obtains when T is equal to Q. This is a kind of Q deformed but unrefined model. And so in this case, it literally comes from the Chern-Simons theory by means of supersymmetric localization again. And so this potential log squared of x is the potential for this refined Chern-Simons theory. So well, it's a separate example, not only because it has a separate physical interpretation, but also because it relates to a whole field of knot theory, since Wilson loops in Chern-Simons, in three-dimensional Chern-Simons theory, produce invariants of knots, so-called knot polynomials or quantum knot invariants. But in our case, we're actually studying a simple case, so which corresponds to, from the point of view of knot theory, which corresponds to just the unknot. So certain functions f of x will correspond to inserting an unknot, so a Wilson loop, which is just a circle, in this Chern-Simons theory. And then when we turn on the T parameter, it will correspond to some knot invariants which come from this refined Chern-Simons theory, some refined knot invariants, which have also been studied in knot theory separately. So this is kind of the context of what we're dealing with. So the idea is that well, we get these matrix models or matrix-like models. Well, I'll just call them matrix models, even though they are actually eigenvalue integrals, first of all, and they're not even proper eigenvalue integrals because they have this Q and T deformation, but I'll just call them matrix models. We get this as a result of supersymmetric localization, but then, well, if we only want to compute the partition function, for example, so the expectation value of 1, then maybe that's kind of enough. We can work from there, but we still actually want to compute the integral. And moreover, usually we want to compute some non-trivial observables, their expectation values. So we need to know how to actually compute these integrals explicitly, preferably explicitly. And so there'll be two ideas and goals, or goal. So when we ask to compute expectation value of some observable, well, we don't actually mean to compute an expectation value of a generic observable. But the point is that for special choices of these functions of observables, the answer can be much simpler, it can be explicit. And it's even better if these special choices form some sort of basis in the space of observables. That would mean that we kind of reduce the problem of computing any other potential observable to just linear algebra, to just expanding it into the basis that we like. And moreover, we want to actually go from analytics, so from computing the integral, like literally computing the integral by residues or something like this, we want to go from this to some algebra. So we want to, if we expect sort of explicit, in a sense, exactly solvable, exactly attainable, we would like to understand what is the symmetry behind this and what is the algebraic structure behind this. And again, this is part of a general QFT idea of using relations between observables. So instead of computing observables exactly, computing them from relations between them. Relations like that are called either word identities or Schwinger-Dyson equations. So we'll see an exact example. And it will turn out that this quantum toroidal algebra is exactly this kind of symmetry behind these explicit answers. And, well, it is actually kind of expected because this quantum toroidal algebra has been shown from various angles to be the symmetry algebra behind this kind of triality or any of the dualities that appear there. So it's kind of shown to be the symmetry algebra behind the HT correspondence, for example. Philosophically, what we'll see is a manifestation of that on an explicit level. So we'll compute the expectation values like exactly, not just an integral form, but we'll get an explicit formula, and we'll see that the quantum toroidal algebra is the symmetry that is responsible for us having this answer. Okay, now let me finally finish with the introduction and proceed to discussing just classical matrix models. So I'll be brief with that, but because things, I hope they're quite simple. So let's start with an even simpler example, not even matrix model, but just a one-dimensional integral. So let's consider what nice way there is to compute moments of the Gaussian distribution, right? So you want to compute the expectation value of x to the n. So one way to do it, the one that will generalize further, is to use relations between observables. So, if we look at this equality here, so inserting a total derivative under this integral, it gives 0 on one hand, well, because the boundary terms vanish because of the Gaussian term. But on the other hand, it produces some relations between observables. So this is exactly an example of sort of word identity or Schwinger-Dyson equation. Well, I mean, in this specific case, already from this recursion, or from this recursion that we get, we can actually compute these and get the Gaussian moments. One way to do it, or another way to do it, is to pack all these recursions into a relation on the generating function. So we compute the expectation value of this exponent, now exponentiated x, so with the parameter t1. And then we do the same. We insert the total derivative. And this now gives not a recursion, but a differential equation on the on this kind of partition function. So this T1 is a kind of current that is coupled to this variable x. Yeah, then we can solve this equation and, well, reproducing, of course, all the known answers. But interestingly enough, if we do the same with the cubic integral, then the equation that we get, so then, well, in this specific case with the one-dimensional integral, there are sort of multiple ways to write things. So, but one way to write things is the following. So, if we compute the equation that appears as a result of inserting this total derivative, it's actually this equation, well, the Ayer equation. The Ayer equation has two solutions, or the space of solutions is two-dimensional. So, we actually cannot find, wouldn't be able to find all the moments of this cubic distribution just from these equations. And the same holds for recursion for moments, just in a slightly different language. Well, and this is clear why this happens. It happens because insertion of this total derivative, it doesn't care about the contour of integration. It just cares about the boundaries of this contour. And in the cubic integral, there are two independent contours such that on the boundaries the integral vanish, but so the integral is convergent on two contours. And these are exactly these two Airy functions. So this is the data which we cannot fix by recursions or equations like this. And so for these exact answers that we're going to discuss, this is important. At least for now, we don't really understand how to. It's not that we don't understand completely how to treat these QT integrals when an analog of this situation happens. Is that at least what I'm talking about is not going to work. So we don't understand yet how to extend these techniques. So therefore, I'm going to focus on cases when the choice of contour of integration, in functions like this is kind of unique. So I'm not going to go into details on discussing like what the contour is. I just want to avoid it. One can do it. One can explicitly describe it. I just want to avoid going to technicalities. But the idea is that in all these cases, the choice there's going to be a unique choice of contour, so such as with the Gaussian, and we're going to avoid cases like this, which correspond to which will correspond to actually more, including more fundamental or anti-fundamental matter. So now let's go to the matrix model. So matrix models, the Gaussian matrix model is integral, almost the same integral, but now it has many variables and it has this van der Monde determinant, which comes from going from an actual matrix integral to its eigenvalues. So this is a Jacobian of this transformation. So and we compute expectation values of function f. So now we have an extra question. Which expectation values to compute? So we have x to the n, but now x to the n can be sort of generalized in many ways. So if so this corresponds to choosing a basis in the ring, or well, in the space of symmetric functions or symmetric polynomials. So the most natural one would be to say, well, there are these functions pk of x, which are the so-called power sums, and then we just compute their expectation value of products of multiple of these things, which are nothing but multi-trace correlators from the matrix model point of view. Well, while it's a useful object and it appears in physics and whatnot, it doesn't work very well if you want to have this. If you want to have an explicit kind of answer for this at any values of this k, else at any value of n. What works instead is to choose another basis, the so-called Schur functions, which I'll not define, but I mean, these are pretty well known. These are just two examples of these Schur functions. So they can be treated either as functions of x or as function of these p. So since these power sums, p, k variables are actually a basis in the space of symmetric functions, we can express the Schur functions in terms of them and just treat the Schur functions as functions of these p variables, like in the examples that I gave. And this is going to be true for other symmetric functions that I'm going to have in the talk. So if we choose this basis, then actually the expectation values take a very nice form. Something called superintegrability happens. In particular, these expectation values are expressed in this way, where this factor, this product of n plus j minus I, is a product over the partition, the partition lambda. J and I are coordinates of a box in this partition. And so, for example, for the partition 3 to 1, this is the product that we get. So it's a nice factorized expression. So it depends on n very easily. And also there's this other factor where we take the Schur functions and we evaluate them at the point where all the power sums are equal to 0 except for the second one. The second one is equal to 1. So in these two examples above, it would mean that for example, the Schur function corresponding to the symmetric partition of two boxes will be equal to 1/2 at this point. So this is an explicit answer for all partitions and all as an analytic function in n. So it is a pretty non-trivial statement that this happens. Well, for the Gaussian model, of course, it is actually. You can actually prove this in multiple ways, and it's, of course, well understood. But the point is that this actually can be generalized, and it holds in a variety of matrix models. Well, again, it's in a sort of special class, but it's not only for the Gaussian potential. That's my point. So. Linear potential would work as well. Potentials that logarithmic potentials that turn out to be sort of Selberg type integrals work as well, and so on. So, well, we'll have more examples in the Kitty deformed case. Well, at the same time, I have to say that there's no kind of complete definition of what superintegrability is. So you might ask, well, maybe for any potential, there is a basis such that this property holds. Well, we don't know how to answer this question yet, whether there exists such a basis or whether it doesn't. Right now, we are studying examples and trying to understand how these examples work. So again, a very useful way to think about this is to turn this all into a generating function. This function depends now on an infinite number of parameters. This is because we need to encode symmetric functions. And so we input these power sums over here, and then we couple each of these power sums to a variable tk, take the expectation value of this. So this should be a g for Gaussian over here. And this generating function will satisfy certain differential equations, just as I explained before, that come from inserting total derivatives. So the only thing that now there's going to be an infinite number of these equations parameterized by just an integer number n. And these are the so-called Virasoro constraints. So another useful fact about this is that, well, since we want, in general, we would like to prove this formula over here, it's useful to expand this. It's useful to expand this generating function in terms of Schur functions. And then it turns out that it takes this nice shape. So each expectation value of a Schur function is weighted with a Schur function itself, but in the t variables. So here the notation is not very good. I actually so when I use the x variables, I mean Schur functions as the symmetric functions in the s variables, but then I use the t variable, I mean this notation over here. So the t variables are the analog of the power sums. These are Virasoro constraints because they commute as if they were in a Virasoro algebra, and actually they form part of the free field representation of the Virasoro algebra. So in the matrix model, we don't get the central charge. Well, it is there. We don't see it because we only get constraints which start from n equals to -1. But we can actually easily identify these operators as part of a full Virasoro algebra that corresponds to just a free boson with a central charge equal to 1. So for the Gaussian model, there is a unique solution to these constraints, as in the Gaussian example with one variable. And well, you can just plug a series ansatz, and then you'll find it. But what we want is to find an exact solution. And to do it, we had to derive sort of algebraic approach. Yeah, I don't want to go into much details. So the formulas here are more to illustrate that somehow it works. The idea is that there is a certain combination of Virasoro constraints, so a sum like this. So we sum t n plus 2 with ln that rewrites in a nice way that allows us to eventually show that there is only one equation. There is only a single equation for the whole partition function, and the equation is actually kind of really simple in the algebraic sense. So the whole operator that acts on this partition function can be sort of brought by similarity transformation to simply d hat, where d hat is just this kind of earlier operator in many variables. And so it is done by introducing, by actually promoting this kind of factor over here to an operator. So there's an operator which I call c hat g, such that it's diagonal on Schur functions, and its eigenvalue is exactly this product over here. So using this C, we construct an operator G, and then the whole equation turns out to be conjugate of just the grading operator by this G, which in turn means that we can easily solve it. So since this is that, and then the only solution so the only object of grading 0 is the constant function. We just immediately show that this partition function is an action of this G operator on identity. So I apologize for having G for Gaussian and G for the operator, but yeah, there are just so many letters. So, well, and then from the form of this G operator, we immediately reconstruct a solution of this kind. So we have that the partition function is actually an action of the C hat operator on a very simple exponent of these T parameters. So, oh, sorry, there shouldn't be a sum over here, right? It's just T2. So, yeah, so there's no sum. It's just exponent of T2, which actually corresponds to this fact that in this superintegrability formula, I had this evaluation of the Schur function in the point delta K2. So I may think of it as if I had the sum over here, but then I just input, a Kronecker symbol delta K2, and then it all gives me just the second variable over here. So it turns out that the partition function is an action of an operator which we know in a certain basis on a very simple function, and this allows us to just algebraically, in a straightforward way, to prove this property. So because we compare this answer that we got with the general expansion. So we match the coefficients in front of the Schur polynomials over here, and this gives us exactly the result that we want. Okay, clear. Yes. So the idea is to generalize this approach to these refined models, and this now would give like an actual substantial proof of more complicated formulas than just the Gaussian. Sorry. So recall that we are actually studying integrals of this form. Sorry, there are quite a few misprints in my slides. I apologize for that. So this should have a label I, obviously. So I just abbreviated all of this stuff that enters the potential by W. So usually in the classical matrix model, we would write e to the minus v of xi. But then as I showed you, this W is some product of Q-Pochhammer symbols, so it doesn't necessarily exponentiate really well. So it's just useful to write it as some function W. So this is how I'm just abbreviating what we already talked about. And then we're gonna consider, like, the working example for this talk is going to be this refined Chern-Simons model with the specific potential. It's just the kind of the simplest case. So that's why. And so, as I said, in the models in question, so I'm going to restrict myself to those models that have a unique choice of integration contour, like in the Gaussian case. And I'll actually say what the restriction is. Well, what is the algebraic restriction in the potential, and what it means physically. And it turns out that for these models, this superintegrability remarkably survives. So if you properly deform your Schur polynomials, and this deformation is sort of known in mathematics to be the Macdonald polynomials. Yeah, it should be Macdonald. They denoted as p lambda of x. This superintegrability survives. So now these are rather complicated integrals, and it turns out that they can, like, certain expectation values can be computed explicitly. And just as the Schur polynomials, the Macdonald polynomials, they form a basis in the ring of symmetric functions. So the formula now goes as follows. So the expectation value of the Macdonald polynomial is given again by some kind of combinatoric factor, which corresponds to a product over all boxes of the partition lambda of some function, but now not of this. So before we had something like n plus j minus I in this example. So typically in this superintegrability formulas, the coordinates of the partitions, they enter in this combination j minus I. So now in this deformed case, they're going to appear as q to the j, well, j minus 1, and t to the minus I plus 1. So this function here, well, what exactly is this function depends on the model, but it's always the same structure. And then over here, we have a Macdonald polynomial evaluated at a certain point in these variables p. So again, it's simpler to phrase this point in the p variables, not in the x variables. And this phi k also depends on the model, but the structure is always the same. Well, for those models for which it holds. So this is pretty remarkable. Well, remarkable for various reasons. For the fact that there is an exact result. The structure is kind of very interesting. The fact that you evaluate an expectation value of a function, and then it expresses through the same function, but evaluated at a special point. So there are some interesting properties of this formula. So for example, in this refined Chern-Simons case, so we have to introduce some notations. So this delta lambda is going to be a specific type of this product over boxes. So delta of x is going to be product of 1 minus x times, and then this combination q to the j minus I, j minus 1, t to the minus I plus 1. And so for the refined Chern-Simons model, the expectation value of Macdonald polynomials has an exact form, and this is actually known as the Cherednik-Macdonald-Mehta identities, which were studied, but obviously by Macdonald-Mehta, but also specifically by Cherednik, and then by Ettinghoff and Kirillov. So this form means that the C function is this delta of t to the n, and then this product over here. And this special point where these polynomials are evaluated is exactly 1 over 1 minus t to the k. So this integral over here has this nice property. So Well, while this specific example was proved, and some other examples, which I'm going to talk about, were also proved previously in the literature, what we did is we kind of developed a unique approach that covers a general approach that covers all these cases, and then prove some new ones. And this approach is basically a generalization of what I talked about the Gaussian model. So, in the same spirit, we construct a generating function for our expectation values by computing the expectation value. Well, we don't compute it; we define this object by the expectation value of this exponent. So now it has these extra factors of 1 minus t to the k over 1 minus q to the k. So these are just needed to match this with this theory of Macdonald polynomials. And now everything is in principle the same, but since we are dealing with these q deformed things, we need to use q derivatives. So here they are. And so, q derivatives, they have all the needed properties, and this allows us to derive the analog of Virasoro constraints, but now they're going to be q Virasoro constraints. So I'm not going to exactly say how they're related to the generators of the q Virasoro algebra, but they are. So actually, and it's good to mention here that from these relations, they have a gauge theory interpretation as well, and they are known as QQ character relations introduced by Nekrasov. And so for example, in this refined Chern-Simons case, this is exactly an operator which gives these Q Virasoro relations. So it's a kind of big expression, but what's important here is that the derivatives now enter in a Q difference way. So these T orthogonal, T perpendicular are just the derivatives in these Tn variables. And as you can see, they enter as exponent of derivatives. So these are actually shift operators, Q shift operators in these variables. So these Q Virasoro constraints, they have been in principle derived before. So for example, for this refined Chern-Simons case, so Luca with Maxim Zabzin has derived them. And actually, Luca gave a talk in this seminar about various peculiarities of how Q Virasoro constraints are derived. But the next task is to solve them. So now we did understand that they do have a solution, but how does one actually solve them? And so this is the question that I'm going to address. Before that, as I said, the constraints a unique solution of these constraints exists only in certain cases. So kind of technically, these are characterized as follows. So the ratio of the potential and the Q shifted potential, so this is Q to the minus 1, should be a rational function such that both of these polynomials have degree less or equal than 2. And moreover, there's a condition on the constant terms. But this physically means that we sort of basically consider models with the number of fundamental and anti-fundamental matter multiplets to be less or equal than 2. And so, the Chern-Simons case also works. So now I'm kind of skipping a page or two of technical computation, but it turns out that the same idea works as for the undefined case, not deformed, where by combining the Virasoro constraints, I can actually write a single equation whose solution is going to be this partition function. And moreover, this equation is made out of differential operators, but differential operators that come from the quantum toroidal algebra. So this is just an example. So let's focus on the one above. It's the one for the Riemann-Simons theory. So here I highlighted things that are operators that act on the space of functions in the t variables. So these other things are just coefficients. So we have this something called x0 minus, x0 plus minus 1, x plus minus 1. Well, then there's just the simple piece, which is an operator of multiplication by t1, which is, of course, also an operator that acts on functions of t. And basically, the idea is to use the fact that these operators come from the quantum toroidal algebra to solve this equation. So I'm going to almost skip these slides. So the quantum toroidal algebra is well defined. There are many names for it. It was rediscovered many times. It's known as the Dinger-Haramiki algebra, as the elliptic-Hall algebra, and other stuff. And as I said, it's known to be the hidden symmetry behind kind of these BPS-CFT correspondences. And so this algebra, the fact that this algebra is there, kind of also comes down to the level of these explicit integrals, the matrix models. And so it has, as an algebra, it has generators and relations. This is just one of the relations. But what I'm going to show are kind of explicit formulas. So this algebra has a representation on the Fock space of a free boson, just as the Virasoro algebra. Again, this just means that I act on the space of functions in an infinite many of variables by multiplying by Tn or taking a derivative in this Tn. So these are my kind of Heisenberg operators. And well, this algebra has many more representations, so less complicated and more complicated. So, but here, this one is important. And so in this representation, for example, these currents x plus minus of z, which generate this algebra, can be represented as vertex operators. So, well, there's a positive part, like a negative, or rather, this is the negative part, the positive part. And then modes of these operators are just certain, well, the coefficients in the Taylor-Laurent expansion of this vertex operator. And these are exactly the operators that appear in our equations. So in particular, it's good to sort of note that this operator, that all these operators, they act in a sort of in a nice way on Macdonald polynomials. Macdonald polynomials form a distinguished basis in this Fock space. So in specifically, this x0 minus is the Macdonald operator, or also known as the trigonometric Ruzhiner-Schneider Hamiltonian. It has a finite n version if we put these t variables to be actual power sums of some auxiliary variables xi. Sorry, again, there's just a lack of letters because, yeah, I mean, these xi's have nothing to do with the operator. But then it's just some kind of trigonometric type of Hamiltonian. So and it's known that this Hamiltonian is diagonalized by Macdonald polynomials with an explicit eigenvalue, given again in terms of these kind of functions that depend on the coordinates of the box in the partition. And well, you can think in both ways, either for it as a function in the x variables or in the t variables. You either use this formula or this formula, of course, up to many peculiarities. Yeah, so let's skip this orthogonality discussion. So just as an example, here's how a Macdonald polynomial looks in terms of these t variables. So if I put q equal to t, then all these cancel over here. This cancel, the denominator and the numerator exactly cancel. and we go back exactly to the Schur polynomials. So in that sense, it is a deformation of Schur polynomials. Yeah. So now, so basically, we reformulated the problem of solving all these integrals into algebraic one. We have an equation in some operator in the quantum toroidal algebra. Well, it's a sum of some basis operators. So in total, it's some operator in the quantum toroidal algebra. And then the trick is to use properties of this algebra to just solve it in terms of operator language. And the solution is basically the same. We introduce an operator, C hat, such that when acting on Macdonald polynomials, it gives exactly this product factor in the superintegrability formula as an eigenvalue. So as I remind for Chern-Simons theory, this is this factor over here. Then using identities in the algebra, which is it's a very interesting algebraic manipulation, but I'll skip it in this talk. There's something called the pentagon identity in this algebra, which allows us to show that this whole operator for the Chern-Simons theory, well, in step one, it allows us to show that if we conjugate this operator by the C hat guy, well, this is done specifically in the case for Chern-Simons theory, we get a much simpler operator. Then, the next step of this manipulation is we actually show that this whole thing is conjugate just to the Macdonald Hamiltonian. So, well, -1. And well, this operator here, we know its eigenfunctions because this is the Macdonald Hamiltonian. We know it's diagonalized by Macdonald polynomials, and we know that the only eigenfunction. So our whole equation will simply conjugate to finding the kernel of this operator x0 minus, and we know the operator with which it's conjugate. So this G hat here, this so-called Gaussian transformation operator. Well, and since we know this specter of x0 minus, then we immediately understand that the only kernel of this guy is just the constant function again. And then, well, we can promote everything. So I kind of explained this in this explicit example of Chern-Simons theory. We can promote everything to a more generic case. So a generic C hat operator and generic point of evaluation. And this is what is going to be the Gaussian transformation operator then. And then in the same logic, we sort of we prove that the partition function is the action of this Gaussian transformation operator on identity, on the trivial function. Well, then, well, since this CM, so imagine this operator acting on identity. So C hat inverse acts trivially, and then we get this expression over here. And then simply by just matching this expression with the generic expansion of the partition function in terms of Macdonald polynomials, we prove the superintegrability formula. So I have to wrap up, and I'll wrap up by showing some examples. So we have a list of, I think, about 9 or 10 different examples, some of which can be actually obtained as limits of the others, but we still want to separate them. So I showed the example of the Chern-Simons theory. So we can have different potentials. So, well, as I said, the number of multiples should be less or equal than 1, or than 2. So in particular, we can take the model, which is like 1 of fundamental, 1 anti-fundamental. This is going to be the potential, W of X. This is going to be the superintegrability formula. And this generalizes the Laguerre ensemble and the Selberg ensemble to their Q-deformed versions. Instead of doing this, we could choose one anti-fundamental method, but couple it to a Chern-Simons term. Then, well, I don't know what to call it, deformation of, but yeah, this is the superintegrability formula. Important examples are with two matter multiplets. So then this is 2, 0. It's the analog of the Gaussian model, is the Q Gaussian model. And then this 2, 2 model, which again is sort of, well, yeah, I don't know. The generalization of Penner models or something like this. So, but yeah, this is the potential over here, and this is the superintegrability formula. And in all cases, it's proved in the same way. Yeah. Okay. So since I have to wrap up, I have a few things that I have to skip, but that's fine. So there are some things that we don't understand fully yet when we have both fundamental and anti-fundamental matter contributions, because this operator that annihilates the partition function now has both. Sorry, this should be T. Now has both x0 minus and x0 plus. But since I didn't get into details, that doesn't really say anything. But anyhow. But yeah, we still can show that everything works for the partition function at least. So well, we talked about computing expectation values, but there is some more stuff. Specifically, since we have some distributions, we can ask whether they are some orthogonal polynomials with respect to these distributions. And well, after we know all this operator formulation, it is easy to sort of generalize all of the stuff and then to construct families of multivariable orthogonal polynomials. So basically generalizations of the Hermite polynomials to some multivariable stuff. So I'll skip that and then I'll just comment. So yeah, in the refined Simons case, what we can match things to what people have done in well, roughly speaking, not theory. And actually, we find that when we put Q equal to T, these equations that we obtained actually have been obtained from some completely different angle. It's called the Skene module, Skene theory, so to say. But there are many questions that remain. So specifically, well, in general, the question is, does superintegrability hold for any other potentials? So specifically for potentials with more matter multiplets. And well, an even more general question is, well, we showed how to go from the potential to this Gaussian transformation operator. But now this Gaussian transformation operator is some object in the algebra. So we can simply ask whether is there a correspondence in the other direction. Now we take some, the quantum toroidal algebra has many more objects of this kind. And then maybe this is a way to, well, this is actually why we're doing this in the first place. Because now we have many more objects of this kind from the algebra, and we can ask whether there are some potentials that correspond to these. And maybe we can find more superintegrability formulas. So yeah, and greater or equal than 3 is specifically interesting because that just, well, it's in the same class of integrals, so we should be able to treat it. And there's some hints from classical matrix models that if you even take higher degree potentials, even though there are these peculiarities with contours, if you choose contours in very special ways, then you can still have these superintegrability formulas. So this is, yeah. So I think, yeah, this is kind of where I want to end. So as a final list of questions, yeah, what happens when the number of matter multiplets is greater than 3? So we should be able to treat this. We should be able to find an algebraic formulation of the problem, and even have the translation of this fact that there are many contour choices, in equivalent contour choices, to some algebraic statement. That would be nice. So orthogonal polynomials I skipped, so I also skipped this question. And there are, of course, many possible generalizations. One direct one is going from these QT deformed models to elliptic QT deformed models. One can go to generalized Macdonald polynomials, so polynomials labeled by couples of partitions. This will modify the integrals, and it has a sort of an avatar on the AGT triality side. And there are many more matrix models. And well, we don't maybe want to take like a completely arbitrary distribution, a completely arbitrary potential, but rather there are many more integrals that come from localization, but many more types of, well, deformations of the van der Monde determinant, of the potential. So this is of course what we're looking at, trying to figure out whether these exact results can generalize these cases as well. Okay, I'll finish here. Thanks for your attention, and I'm sorry for going a little bit over time.
Thanks a lot, Victor. Okay, let us thank Victor. Okay, questions?
I have a question which is not directly related, but which of the techniques which you described may be useful for a matrix model related to n equal to four-dimensional theories? For example, n equal to supersymmetric theories. They have potentials which are quite non-trivial, which follow from localization, the matrix model. So there are some Toda-type-like equations which sometimes could be used, but that looks very different from what you were discussing. So I think these models which you discussed are kind of simple in a way, but though the measure may be more complicated, but it's kind of trading one for another. Could you?
Yes.
Yeah.
Yes. So yeah. Well, for obviously there is a theory which is very simple in this it's kind of simple in this regard, which is the n equals 4. There the measure is just the van der Monde and it's just the Gaussian model. So everything that I talked about holds there. But then yeah, so the idea is that, well, we have this van der Monde squared and n equals 2 four-dimensional theories. They introduce some generalization of that. So we have some generic, well, not generic, but there are some functions of like some products of some function that depends on xi and xj. And indeed, well, so in principle, going from van der Monde to this Qt van der Monde is already kind of making this function more complicated. But I agree that those functions that appear, so in n equals 2 models, I think these are expressed through some Barnes G functions, and so these are indeed a bit more complicated in that regard than the Qt, than the Qt van der Monde. So well, for now there is nothing I can say from the perspective that I was talking about these models. But, well, I mean, yeah, there is no guarantee that, of course, any of this generalizes to these examples, but I would assume something does. So as practice shows us and as our experience grows, we understand that if you substitute the van der Monde for another type of measure, what you should do in the level of these symmetric functions is to change the type of symmetric function that you're talking about. So Schur polynomials and the van der Monde were directly related because the Schur polynomials themselves are orthogonal with respect to integrating with the van der Monde, right? It's just a Haar measure. The Macdonald polynomials are those polynomials that are orthogonal in themselves, integrating them against the Qt van der Monde without any potential. So kind of the first naive step would be to ask, well, can I define some sort of symmetric function that is, or a quasi-symmetric function for that matter, that's fine as well, that is sort of orthogonal with respect to these measures? That would require like learning beyond any kind of large N approximation. So we want to know like how how to take these integrals, maybe involving some contour with some residue type calculations, but at finite end. Yeah, so this is completely unknown for now, but I think this would be a promising place to look for.
Okay. Thank you, Victor.
Thank you.
Questions? Final chance to ask questions. Going once. Going twice. Okay, perfect. So Victor, thank you again for your presentation. It was it was slightly a bit technical for me, and I've kind of got lost in all those integrals, I think, on the slide number 3. But yes, well, good luck, and hopefully we'll see you again at our seminars.
Yeah, thanks for having me.
Yes, it's a pleasure.